Well, I think we can start in just a moment. Now it's much better. Okay, so I think we can start. We have some people here at the room, and we have some people at Zoom, and I hope also on YouTube. Today, the second lecture of Irina Schreiber, so I already introduced her, and it's my great pleasure to see her here and to see you here in this room at the Department of Physics of Tom State University. And today we are going to listen and discuss special relativity without equations. I guess it will be challenging, but Irina, the floor is yours.
Actually, this is what I think. It will be quite easy. Why it is first? The first thing is why it is in English, in Russian university, right? Why do we do it in English? Because I said it previous time. What is the language of science? English. What is the language of physics? English. One day we'll start to speak Russian all around the world, or Chinese, but nowadays to discuss science we speak English, and this is the most important thing. So everyone who is in a scientific department, and especially physics department, should be able at least to understand it in English. Second thing, I will try to speak slowly, but when I'm looking at you, you guys should be quite familiar with the language and should be able that I speak very fast, and it's difficult to stop me, but nevertheless, when I start to speak too fast, don't hesitate to interrupt me and slow me down. And the third thing, why do we do it in English? I want these 27 kilometers of Large Hadron Collider and laziness of physicists to walk around. So I am the biggest representative of lazy people. I usually give these lectures in English, and honestly speaking, my career in high energy physics was all the time in this language. It started in this language and it continues in this language. And for me, as for many of my colleagues at CERN, it's actually our common problem. We have difficulties to speak about physics in our native languages. I can speak about that in English. I can do that in French, because sometimes I give lectures in French. But in Russian, this is, even though that is my native language, this is the most difficult task for me. So, English it is, and today we'll have really the introductory level to the special relativity, and I'll try really to avoid formulas and equations. Cannot avoid it completely, but we only scratch the surface to understand what it is about, to get the preliminary idea and where it leads us in general. Why special relativity? Why it is important? We'll talk about electrodynamics tomorrow, and I will talk a little bit about that as well, but it's a huge part of, actually special relativity was born thanks to electrodynamics and thanks to speed of light and Maxwell equations. So it comes all together and you cannot forget about that. It's changed quite a lot our understanding of physics and how do we do calculations, especially with the tiny objects as elementary particles. And as well, the thing is, we need to understand that when we deal with our accelerators. Which way? So, first of all, before we go further, I give you 3 words, Okay, it's actually 4, but 3 terms. Airplane, airport, and bad weather. You keep it in your mind. At the end of this lecture, we come to that and we'll discuss. You will give me the answer what it has to do with the special relativity. Maybe you know the answer already, but then you will tell us later. But nevertheless, it all has to do with the special relativity. So climate projects, it's not only about big data or high energy physics, it is about theory and special relativity as well. I know that you have books in Russian about that, and usually what I mentioned already, and on Monday, it's quite good. They're quite good books, but they are sometimes too overcomplicated for the beginners. So when I recommend to my students some books to begin from, a beginners or freshmen, these are usually the books which I recommend. The last one is actually Introduction to Physics of Particle Accelerators, and it covers more. It covers accelerators and physics as well. This is like the most popular book in particle accelerators, and I think you have 1,000 copies of that at CERN. It covers more than special relativity, of course, but it's a really good book for that. So, what we'll be talking about today? Oh, really simple thing. We will start with transition, which led us from a Galilean relativity to special theory of relativity, and how it came to our vision. We came to the most important things, very simple, but most important in all of that, which we have really to understand, not that much by formulas, but a lot by thinking about that, how we take it, how do we understand it, and then consequences, of course, of these postulates. So, a long time ago, when we still thought about all of that, about motion only from point of view of Newton, and all was described by Newton laws of physics, and as well it was postulated actually first of all by Galileo. Simple as that. The motion of bodies included in a given space are the same among themselves, whether the space is at rest or moves forward in a straight line. This all of us, we know all of that, right? We have a reference frame, fixed frame, point X, Y, and Z. We can call it, our reference frame. We get our moving frame, X prime, and we put the coordinates with a prime factor, and then we can easily calculate all the coordinates, prime coordinates in the moving frame with these equations. I think all of you know them, and it's easy to calculate with the Newton mechanics, and nothing else is needed. And actually what I want, it's no pointer, I want you to look at that. It's a very simple thing, but just the way it looks like, the coordinate and the velocity and time. This is the only factors which we were using during Galileo time and Galileo transformation. And then what happens? Then in 1905, and we'll talk about that tomorrow during electrodynamics course, Maxwell comes into our view. Maxwell equations, I like how it looks like on this slide. It's Maxwell, more or less, I think, whatever it means. T9 translation probably, but good to notice, but whatever. So Maxwell equations, we don't stop on them today. We will talk about that tomorrow. but what it talks to us about, it talks about electricity, it talks about magnetism, and the most important thing which came out of Maxwell's study is what? What was the most, those of you who knows anything about Maxwell equation?
It just was the first unification between electricity and magnetism.
Exactly, this is a very important point. This was the first unification. And what was the consequences out of that? What he discovered and he unified electricity and magnetism.
I guess Joe just...
Someone is talking there, no?
Yes,
Oh, it's me. What?
It's really... I have no idea.
Whatever.
Maybe, I guess, I really don't remember. He just calculated the speed of light using it.
Exactly. Exactly, because he unified electric and magnetic fields, and he came up with the conclusion that the speed of light is the same. It's really a constant. This was a very amazing discovery, and it came out actually of this equation, which gives us very strange conclusion to Galilean transformation, right? So it's always the same. It shouldn't change then. Then actually what is happening then, that if we take Maxwell equations, if we represent them as a wave, don't keep any attention to equation there, even though that is a simple wave equation, but if you transform it with the Galilean transformation, you don't come up with the same thing. It means, in this sense, if you look at that if you have, I don't know, spaceship traveling in the space, or standing on the Earth, it would have one physics law. When it's traveling to the space, then it would happen to have a different physics law. So it's like, as soon as it starts to move, it's not only that it's moving, but it has different physics law. Is it true or not? So actually, quite a weird thing, right? So this was the first thing which was giving a thought that probably something is wrong with Galilean transformation. So, this is actually was the consequences of Maxwell equations. What the heck happened with Maxwell in here? I really should have a screenshot of that, because I like it and I hate it. Yeah. So then whatever is disturbance of the field, whatever is the condition, speed of light was staying the same. And then even if the disturbance, even if the object which creates the disturbance is moving, speed of light is still the same. It's like if we take, I don't know, the simplest example, a train, and we put a flashlight on this train. So train, let's say that flashlight emits light with the speed of light, and then the train starts moving, and train moves with half speed of light. So what would be the speed of flash then, of light?
It would be also the speed of light, because
It would still be the speed of light, right? But if we calculate this way, it should be 1.5, which doesn't exist. So all of that puts us into the conclusion that something is wrong. There are many experiments made to prove or justify. One of thinking at that time, it was that there is a special ether in which Earth is moving and in which light is propagated. And if the light is propagated along this ether, then it has a certain speed. So taking that into account, you can check if the light is propagated along or it's perpendicular. This was the first experiment which tried to prove that there is ether exists in which a light is propagated. Michelson-Morley experiment, and actually there were more or less like light object interferometer, and they were measuring the path of light along and in perpendicular way. And then they started to calculate the speed. At the time, actually, they came up with the conclusion, but it's the speed of light is still the same. Nothing changed. And either there is no ether in which light is traveling, or something again is wrong in the calculation. What happened at that time, because the experiment was done to detect the ether, to detect this space surrounding some substance is in which light is propagated, to prove its existence. And the experiment is actually failed. Yeah, so they were really disappointed by that. But, and they discovered that the light is traveling with a fixed and constant speed in any medium, independently on in which direction it's traveling. And it was unlikely, like not anything else on the Earth, because when we apply to cars, to moving objects, everything was in Newton mechanics. And for light, no medium is required to be disturbed or to be propagated. It can go like that. So the very important lesson which was learned at that time is what experiment is failed, but if it wasn't failed, we wouldn't come with a special relativity theory. And this was actually Albert Einstein who said, if they hadn't brought us into a serious embarrassment, and it was kind of embarrassment at the time, no one would think about regarding the relativity theory as a halfway of redemption. It's actually, when we talk about Einstein and relativity theory, what is a special relativity actually in this sense? If we take Newton physics, as we were talking about Maxwell equations already, we take Newton physics, we apply Maxwell equations to that, we combine them together and try to find a common solution, try to make them to work together. So then we transform Maxwell equations from fixed frame to the moving frame. They should stay the same. If we manage to come up with some solution, we come up with special relativity. But special relativity deals with inertial frames, meaning not accelerating frames, right? So we need to apply something for a general case. Plus, we have gravity, which is not taken into account in the special relativity. So to take gravity into account and to deal with any type of frame, with any frame, then it was another theory of Einstein, which is called
General.
Bingo. Yeah, it just, again, simply to understand what it is about. We sometimes using these words, special, general relativity. But what is behind that? There are quite simple physical laws and issues behind that. Yeah, Newton laws, speed of light, Maxwell equations. Add gravity, add acceleration, you get general relativity. As simple as that. Someone doesn't like special relativity, I think. Not. So, then actually there was Lorentz who came up with some other transformation. He was trying to work at the same time as other guys when we were still talking about ether. And when we thought that there is ether existing, but at the same time, we could see that it doesn't work. So, and the Maxwell laws, they are not adapted properly. So, at the time when ether wasn't disregarded yet completely, Lorentz came up with some conclusions, which actually was implied later for, I think, some billiard or whatever, something like that. But nevertheless, he was talking about that mechanical bodies, he was thinking about ether still, that it's existing ether, but to adapt it to speed of light and non-changing speed of light, he started to sense like bodies actually would compress, become smaller in the direction of moving in ether, with a description of the process. So if the body moves very fast, it would contract, it would become smaller, and from one, if we look at this transformation from one frame of reference to another frame of reference, the same thing would happen with time, and we would have a mathematical description of time as well for that. And actually, when I say mathematical description, he came up with the Lorentz transformation, and you see he's talking here in parallel, like moving along the ether, which doesn't make any difference later for us. But let's take a look quietly on that. We take really the Galilean transformation and we apply a special factor. C is the speed of light, and let's see the calculation. Let's see if we have the speed equal to the speed of light, right? There it will come to almost to infinity, right? If we have the speed very, very small compared to the speed of light, the factor in here, it would be almost negligible. We would divide by 1, so we will come up again with Galilean transformation. So you see, we apply this factor everywhere in here, and if we come up with Newton motion, with a normal motion, we don't touch speed of light, we don't touch high velocity, then we go back to what we have with Galilean, which is perfect, right? We kind of satisfied everyone in here. So, and actually it was already Albert Einstein who looked on the experiments, he looked on the Lorentz transform, and he postulated two the most important principles of special relativity. The laws of physics, the first one is the special principle of relativity, that the laws of physics are not changing, they invariant in all inertial frames. And actually, this would fit us, right? What I said about moving spaceship. Wherever it is spaceship on the Earth or on the Moon, it would still the same, and our astronauts are still intact, or at least they are touched by the same physics law. And the speed of light, still the same. Always we forget to add it, but we have to remember that when we talk about constant speed of light, and the number we all know, we talk about speed of light in a vacuum. And then we say that a speed of light cannot be, nothing can move faster than the speed of light. Numerically, when we talk about medium and object traveling in some medium, we can get numbers which are higher than speed of light in vacuum, but this is an additional point. We are talking about the same frame, the same condition. We are talking about speed of light in vacuum. So, continue further, let's define very important things, definitions in physics. Event, frame of reference, simultaneity, and speed of light. Why I want to stop in here? Because quite often we talk about them, but we don't really understand what is behind. What do we mean by that? And actually these are the very first level, the basic level of definitions, and very simple. Event is anything with a location in a space and time, which is happening, in these coordinates and at this time. Let's take quite simple example. Here we have our clock, 12 seconds, and we have our coordinates, just one dimension, and it's in meters. This dot, yeah, has a coordinate 0 meters and at 0 time, 0 whatever minutes or seconds, whatever we define in here. So now tell me, define me this dot. What is this event? Give me the definition of this event. 2 meters, 2 seconds. Okay, good, exactly. So this is a definition of an event. If we come back to that, yeah, the coordinate can be, 3 vector, and then the fourth one is a time. But event, it's always with definition in space and time. This is what we call event, nothing else. Frame of reference, any object of those parts are moved with the same, at the same velocity with respect to an agreed upon reference point in space. So we take one point in space and all the objects of this frame should move with the same velocity. We are talking about frame of reference. We are not talking about different objects inside of frame of reference. Frame of reference. You understand the difference, right? We define our reference sample, our reference point, so frame of reference. Now we have black dot, our reference, and do blue and red dots share the same frame of reference or not? Why not?
Because black is not moving.
No, black, okay. Black is defined just as a point, but now blue and red, you have definition like you add moving parts. So no, this is okay. I mean, you can add it. It should, if we take blue and red all together, they are moving. Do they move the same or not?
With respect to what?
With respect to black.
Okay, they are moving. They are have the same frame of reference.
Mm-hmm. Yeah, because they have the same. This is the length of the arrow is velocity, right? So the direction is the same, and they are moving with the same. I mean, it's there is no number in there, but this is the same length. But now, is the same or not? We are talking not about objects inside of frame of reference, but frame of reference. Blue and red. It's the same or different frame of reference?
It's also the same.
Another, I mean, why? Yeah.
Because if I'm taking blue, for example, moving in the positive direction of the black reference of frame, and red moving the same direction on the opposite direction, also with respect to my reference of frame.
Yeah, but here, if we talk about frame of reference, it has to move with the same velocity. And even if the direction is opposite, it's already a different velocity. Yeah, it's a minus sign. So, in sense of frame of reference, they are different. Okay? This is what I try to point out, that of course, if you define objects, you take one frame of reference and you describe objects within that, then yes. I mean, we all already define our frame of reference and then we described objects inside of that, then it doesn't matter. But if we are talking about frame of reference, they are different. Okay? So, simultaneity. There are two events which are happening at the same time. Quite easy, right? Nothing very difficult. At the same moment of time, good. But the point is, it has to think from which point of view. If they happen at the same time, in which frame of reference and for which observers. Right? If we look at that, I will have it later. If we think about person standing on the ground or person sitting in the car and watching the same event, right, happening on the street, they would definitely have it differently, especially if we move away from Newtonian speed and we go to relativistic speeds. We'll have an example of calculation later that it would be quite different. Bam, bam, bam. Speed of light we discussed already, that it's the speed with which light travels in vacuum, and it's always the same. Actually, the first attempt to do that was done by Galileo, and what he was doing, he had an assistant, and the assistant was standing on some hill, and was they were opening and covering a lantern with the light. Unfortunately, or fortunately, person are not moving with the speed of light, so the way they were opening or covering this lantern, they could not really calculate the speed properly, they could not detect it. It was a bit later when it was calculated. It's not that much later after Galileo. It was calculated through Jupiter moon, I think, first time the speed of light. And the precision with which it was calculated at that time already was around 50 kilometers, yeah? So, which is quite a good precision. And you don't have all the measures which we have right now. I'm always going. So, let's go back to a little bit to Lorentz transformation. Beta, it's usually how we write the velocity in high energy physics. It's really relation between the velocity of the objects and speed of light. And then we define the gamma factor, which includes, you see, this is what was previously I was showing you, this is just a square of this ratio. And then we can rewrite these equations in this way, yeah? And then what we see, if you look at them, remember I was telling to you, remember this x minus vt, what was in Galilean transformation. Look, it looks very similar. It's basically the same thing, physically, yeah, it's the same formula. It was we have in front of that gamma factor, this Lorentz gamma factor, which will change for us the coordinate and the time. Huh? So, and this is how we come with length contraction. Lorentz, what I said already before, said that the length of the object, moving object, is contracted, but actually it's not the length what is contracted. This is the way how we measure it in the moving reference frame. And this is, you see, this is a gamma factor relations. And again, if we have a gamma factor, if we look at that, how we define a gamma factor in here, yeah, back in here, remember what we were discussing before when I was pointing out to you, when we have low speeds, yeah, this comes to 1, and then we don't need to take it into account, and it will be x prime, delta x prime will be delta x, so it would be the same. The same thing happens with the time. Just to see it more intuitively, I think many of you have seen this picture at school, right? When we have the path of light, when we have a fixed train, or we have a moving train, and depending on the person of the observer, if he is inside, how he sees it, or he is outside, and what would be the distance. It's quite easy to see that on this picture. Good, another very good example. Yesterday on Monday, we were talking about muons, which are traveling in half lifetime of muons is around 2 microseconds. Yeah, and if we calculate, and they created 12 kilometers above us, and then if we calculate how long they will live until they decay, it would be around 600 meters, but they do reach the ground. My first experiment, when I was still assembling CMS experiment, the first paper, internal paper we were writing, we were measuring muons, muon rays. We could actually see them, we could actually detect them, how this happens. But the thing is that muons, they are moving approximately with the speed of light. It's like 994, something like this, really close. You can basically calculate, 994, it's written in here. So, and you calculate the gamma factor for that, and then you see that actually the distance in this frame reference, it can be different. If you think about that, muon decay, a half-life of a muon, it's calculated in which frame of reference? Of a muon. Okay? It's his own or its own time of life. It's calculated in a frame of reference of this particle. But the 12 kilometers distance, it's calculated in a frame of reference of Earth. So we are mixing up two frame of reference. So, and if we start to calculate all of these properties, either in one or another, so what we will get is a muon has more time to travel, or the distance is not traveled. So you can recalculate it different time. You can try to do the calculations on your own, trying to use this number. This is all you need, 2.2 and the speed of, look at that, how it will come out, how far muon will travel. Do the exercise, because it's a very easy thing to do, but it shows to you that it can travel much more than 12 kilometers. So, just to clarify another time, matter is not contracted. If I'm moving really fast, I'm not become slimmer or shorter. It just, the calculation in this frame of reference will be different. Yeah, space is modified, and the clock is not changed neither. Clock is still the same as in Tomsk or in Geneva, but it's time what is modified, how we calculate it in there. And actually what Einstein did, he didn't calculate anything. He just believed in that and postulated in his theory. Things which we define quite often in high energy physics is mass, and the proper mass is a mass of body at rest. Whatever we see in our books, it's mass of body at rest, because as you see, all of that can change when the body starts to move. Time, it's measured in its own frame, as muon, right? We measure its half-life in his frame of reference, its own frame of reference. Otherwise, it has to be recalculated. And the length as well, when we measure it in its own frame, when we measure the length in the frame of Earth, it's one thing. When we try to take muon into account, we have to recalculate it because it will be different. So, again, one more time, just to remember, because this is the most important thing in there. Laws of physics are invariant in inertial frame of reference, and the speed of light always the same. So let's take on the consequences of these two important postulates. We know now that they are all the same, and this is really good. We don't have to adjust anything as if we travel to Mars or to Moon. But if they are the same, and if you talk about the objects inside of its own frame of reference, you cannot say it's moving or not, it's standing or not. So you have to have recalculation from one to another. So there is no absolute thing, like state of rest is not an absolute thing anymore. For me, it's in the rest. For some other frame of reference, it's moving, and vice versa. All motion is relative. And the same thing, we agree that the light, for the second one, we agree that the light moves with a certain speed and it cannot be changed. But at that, with that conclusion, we have to come to the thing that time or space, so both of them experienced in the same way by observers in different state of motion, must be abandoned. So we don't experience, there is no such a thing as an absolute measure of space or time. We have to agree how which frame of reference we use. But the only thing, the light is constant. So space and time are not independent. No speed of moving object can exceed speed of light in vacuum again. Simultaneity, we have to think about that, what it means, and there is simultaneity only can be observed in the same frame of reference. We have to remember about contraction and dilation and apply gamma factor each time we address relativistic velocities, relativistic speeds, and there is no absolute speed or time or space. These are,
So when we're talking about the Lorentz cofactor, I mean when the speed is much
higher
than the speed of light, it will be I cannot calculate. It will be just the same law.
It will be the same,
Yes, but I mean that works for every law in physics, that in low speeds the Lorentz cofactor will be also negligible.
You can look. The thing is, as I showed to you, right? You can always use that. It just, when you calculate it, when the speed is much below speed of light. Imagine here, let's say 60 kilometers per hour, and 300 per second. When you divide by another, this factor is so small that this will be almost equal to 1. So you will come back to the Galilean transformation in Newton. No, so you can always apply that. You can always use that. It just, you know that it's not needed in a normal life. The thing is, it's always a question, where do you start the balance, where do you need this precision and you need recalculation, usually when we're close to the speed of light, but as I said, you can always use this factor and you will be precise when you're using that. You won't make any mistakes calculating normal movement of objects, is that. This is just, for you to have the formula which are used. We are not going through that, even though that we went through all of that proper mass, rest mass, and then how you recalculate energy, total energy of the system. You have to take it into account. How you recalculate momentum of the particle. What is a gamma factor? How we define the velocity in high energy physics. It's just the simple thing what we use to have simple definitions, which we used to have in high energy physics. It's just to show you for LHC, gamma factor is huge, almost 8,000, 7.5. So imagine how much it will influence our calculations, right? Did I go in the rust? This we can, This is, voila. And here we are. Now, I mean, this is, don't keep any attention to that. It's actually, we should have had it in the other way around if we had already calculation of magnetic and electric field, but doesn't matter. It's, if you want to take a look at that, this is just how we apply to electric and magnetic field our gamma factor. But we'll talk about that tomorrow a little bit more. But what I wanted to ask you now, when I said to you about bad weather and planes and airports, what did I mean by that? How it is related to the special relativity? Any idea? Think about speed, movement.
We can say the airport here is our frame of reference for the plane.
Another ideas? Especially with the bad weather in Tomsk, you have to land. You should know talking about clouds and how you have to travel through the clouds.
I can adapt something. Special theory of relativity is profoundly used when it comes to anemometry, that is measuring the speed of the wind. for example.
With Gleb, right?
Yeah.
Yeah. Gleb, yes, but what do you, okay, wind, how to...
It's used mostly because you utilize Doppler shift in order to calculate it. And Doppler shift is a relativistic effect.
You're thinking too far, Gleb. I think it's much more simple. I will show that to you guys. We have satellites, okay? Bad weather. We have to land our plane. We have all these mirror clouds, whatever. Everything is covered. Foggy day, you cannot see anything. Satellites, which was used again first for military purpose, cost billions of dollars, right? And they are moving with quite a high speed, 14,000 kilometers per hour, 20,000 kilometers above us. So if we get an information from this satellite, so if we actually don't apply the effect, now, okay, so if we start to calculate beta, the velocity, yeah, and we start to calculate the gamma factor, effect from special relativity is not that big, but it still counts. If we apply in addition a general relativity and effect, then we come to the factor of something around 2 kilometer differences when we land the plane. Okay, if we miscalculate the distance, we miscalculate the speed, we miscalculate the time. So what does it mean? Instead of Tomsk airport, you end up in whatever, I don't know, Kolpashevo or something like this. I have Novosibirsk, yeah, even good if Novosibirsk at the airport, but the thing is you need to know the precise location. As satellites, they move with a high speed above the ground. You need to recalculate it. You need to take the aspect of special and general relativity into account to bending of the fields in there, yeah, and gamma factor. Then to understand where you have to land your plane. So when we talk about what I was telling to you on Monday, when we talk about high energy physics and medical applications, right? Or quantum physics and quantum computers, we do find practical applications. Again, guys, what we were talking to you about, what is a practical application of our fundamental research? Yeah?
May I just go one step back?
Yeah?
Is this the reason why every day, I forgot the name, but they use special clocks? We know one of the elements in the Mendeleev time. We know 1 second and the atom, how much times it trembles in 1 second.
This you need is, yeah?
And every day, because they are traveling really fast, we gotta reclock it.
Exactly. We lose together, yeah, exactly. This is it. There are two effects in there. The first effect, which would fasten it up, it would be a general relativity effect and bending of the field, and the special relativity effect, it actually will slow it down because, yeah, time dilation and gamma factor. And then you take these two into account, yeah, you have to recalculate, remeasure your time,
to
yeah?
turn the clock back, to turn the
Or front to back.
Yeah.
Yeah, exactly. This is the thing, and this is how you have to calculate. Of course, how they do with satellites, they put more satellites, they recalculate, they calibrate the time and set the frequency in the proper way. But actually, this is a theory, right? This is just a theoretical thing, but you use it in a very practical application on everyday life. For those who are flying quite often as I do, it's actually quite a useful thing. And this is perfectly on time today. Very simple. Slow English, I think. I tried to be slow. And this is just a scratch of the surface. And the main thing you have to remember in here, I think I repeated it already 3,000 times. I repeat it one more time. Two postulates of Einstein.
It lies invariance, and we can say it's symmetric. Every known physics works in every
Yeah, they are as well invariant in any system. And yeah, and you have to take Lorentz transformation into account each time you come to relativistic speeds, especially when you deal with high energy physics. That's all for a moment. Very easy. No formula, basically. No formula, as promised. But the idea for you, of course, there are more. When you really learn it at the university and you go to the whole course, there are more applications for different processes because we are just having here the basis. But this is the basis of everything. This is the first step where you come and you need to put it into a calculation of any field you calculate, of any formula you calculate in when you deal with high energy physics. Done? Questions?
You said that speed of light cannot be changed. Yes, it's postulate.
Yeah.
Some kind of.
In a vacuum.
If we imagine what could be if speed of light would be a little bit tiny.
You mean, let's define what do you mean by that? You mean if our measurement of speed of light can be redefined of...
Truth speed. What would be if it will be a little bit slower?
But it would be, the thing is, it would be the same, I mean, if it's would still the constant, okay?
Still constant,
But the
a little
same,
bit slower.
we would, I don't think we would redefine our physics. So this is the thing is, this is just a number, okay? And depending on what you, I don't know if all the phenomena would stay there. It would be just the number which would be smaller. If we are talking about that it would be changing from depending on the condition, then it's a different story. But if it's the same all the time, it's just the number is different. The number is only our definition, right?
For example, if our speed of light will be slower,
life will be slower.
Yes, light will be slower.
Okay. You wouldn't notice that.
Light from our Earth will gain.
Whatever light from the end of the galaxy would come to Earth much later. But you wouldn't notice that. Okay, you wouldn't notice the effect.
Yes. Another thing.
You mean we would become colder?
No, maybe colder. At first approximation, for example, the wavelength of waves. There is we have some formula where is lambda wavelength. It's c.
Hc divided by energy, yeah?
Not hc, just
Planck constant.
No. Lambda
is equal Planck constant multiplied by speed of light divided by energy.
Yes, it's true, but if we calculate through frequency.
Okay, but it would be just, it would turn it around.
Does it mean that our wavelengths will be shorter?
Speed of light would be lower, right?
Yes.
I mean, if we have the same energy, it's just a mathematical equation. We forget, we take a speed of light. 10 divided by, and here is lambda. Let's say 9 divided by, which is bigger?
Yes, that means that we will have the shorter wavelengths, yes?
Yeah, so?
But if we will have a shorter wavelength, for example, red wavelength is 790 parameter, red wavelengths
Would be shifted, you mean?
shifted, yes. That's first approximation.
You're talking about Doppler effects, yes?
No. Just
No, he is talking
Slow
about
down.
if everything overall will be slowed
Yes.
down and we would shift it. The thing is in these randas, what I would imagine at the end, all of that, if the phenomenon is the same, all of that is our definitions, right? So we would, what is red? It's not the red. I mean, we
red
defined
is-
it, yeah.
Yes.
You would shift
Just
it and
wait
yeah.
more.
And you would redefine. If the phenomena is physical, the phenomena is the same, it would stay the same. For us, we wouldn't notice it in our frame of reference.
But if we just take our eye, yes, our eye now can see from
Your
the
eye would be different. You're talking about that, yeah, you're slowing down, you're reducing the speed of light, but you want to leave the same,
Yes.
okay? So observer would change as well, right?
Yes.
Everything would change in this sense. Because again, it all depends when we start to talk about objects and about matter and about us and about creation of us and what we were talking on Monday, what CERN is trying to understand, how we all were created. So we were all created with electromagnetic phenomena, right? And if the speed electromagnetic phenomena gives us, yeah, the speed of light is this the same from all points of view. And if it would be different, just the number-wise, it would be just defined, I mean, everything would be defined differently, and you would be defined differently because you consist of these elementary particles.
Thank you.
You can go home.